do you get from here to Mars? How do you get from here to the moon? Probably more important to you, how do you get from here to your home? Well, to start, the answer to all three is very similar. You need to know where you are, you need to know where you're going, and you need a map that can connect the two. Now, in the case of going home, your map will have all of the roads between where you are and where your home is, so you can pick your path or your trajectory and drive your way home. In the case of going to Mars, or to the moon, or to any of the planets or planetary bodies where we've sent humans or robotic spacecraft to over the years, finding that path or that trajectory is proved all the more difficult because where you are and where you're going are always in motion, which leads me to orbits and trajectories and NASA's return to the moon. Merriam-Webster defines an orbit as the path described by one body in its revolution about another, like the Earth going around the sun, or in the case of this talk, a spacecraft going around a gravitational body or two. Now we enter the world of rocket science. Johannes Kepler, with the help from volumes and volumes of data on planetary motion captured by Tycho Brahe, calculated that the paths these orbits took in the presence of a gravitational field followed conic shapes like circles or nearly circular ellipses. And with this information, scientists figured out how to move an object, a spacecraft, from one orbit to another. One of the most famous of these scientists in orbital mechanics circles is Walter Hohmann, who created what became known as the Hohmann transfer. The Hohmann transfer, simply put, is an elliptical orbit that will allow you to transfer between two circular orbits of different radii in the same plane about the same central body. So remember when I asked you how you would get from here to Mars? Well, the Hohmann transfer from Earth to Mars, shown in this animation, would take you there. NASA's scientists and engineers have gotten really creative in creating trajectories to send robotic spacecraft around and beyond our solar system. But for humans, the farthest that we've gone is to our moon, 50 years ago. In Apollo 11, on July 16th, 1969, 3 astronauts were launched on a Saturn V rocket, leading to humankind's first giant leap. After the first 3 Saturn engines burned, the Apollo spacecraft was placed into a low circular Earth parking orbit, roughly 100 nautical miles in altitude, or approximately the distance between Cleveland and Columbus. After final checkouts, the Saturn V burned what's called a trans-lunar injection burn, or TLI, that placed them on the trajectory that would take them to the moon. There they would coast for 3 days before being captured by the moon's gravity into a low lunar orbit. Now, after they completed their surface mission, the astronauts returned to the waiting command module Columbia to start their trip home. The Columbia, like the trans-lunar injection burn, burned a trans-Earth injection burn to place them on the trajectory back to Earth. Now, having traveled an average distance of 240,000 miles from the Earth to the moon, these Apollo missions still stand as the farthest that humans have ever gone from the surface of the Earth. And this is a significant distance. Given the diameter of the Earth, roughly 30 Earth-sized planets can fit between the Earth and the moon. Now, since Apollo, the farthest we've sent humans is to the International Space Station, located in a low Earth orbit, roughly 400 kilometers from the surface of the Earth, or about 250 miles, or approximately the distance between Cleveland and Cincinnati. Now, because the International Space Station orbits so close to the Earth, the combined gravitational pull of the Earth, as well as the atmospheric drag on the station, means it's in a constant state of freefall and reentry. And periodically, visiting vehicles with propulsion systems will give the ISS a boost to keep it in its orbit. Now, with this spring's Artemis announcement, NASA has announced plans to return humans to the surface of the moon, landing the first woman and the next man on its surface by 2024. The current Artemis plans are a blend of those Apollo lunar sortie campaigns as well as the ISS sustainability elements. And the first key sustaining piece of this Artemis program plan is the Gateway, to be assembled in orbit near the Moon. The Gateway is a mobile command and service module, and it will provide us with a place to aggregate and assemble the spacecraft that will land onto the Moon, as well as provide us with a communications relay to support robotic and human missions anywhere on the Moon's surface, but starting at the Moon's south pole. The first element of the Gateway is the power and propulsion element managed here in Cleveland at NASA Glenn Research Center and built in a public-private partnership with Maxar Technologies. Now, said our administrator, Jim Bridenstine of the PPE, it will be the key component upon which we will build our Lunar Gateway outpost, the cornerstone of NASA's sustainable and reusable Artemis exploration architecture on and around the Moon. This power and propulsion element is a high-power, 50-kilowatt class solar electric propulsion spacecraft. And at that, it's roughly 3 times more powerful than current state-of-the-art technologies. Now, the Gateway with this PPE, with both power and propulsion, is capable of not only holding place in one orbit, but of transferring between orbits in support of the sustainable lunar architecture. Flying the PPE will provide us with invaluable experience for future missions to Mars. And the current plan is to launch the power and propulsion element in 2022. The Gateway will be assembled in a new type of orbit, perfectly balanced by the gravitational pulls of the Earth and the Moon, called a near rectilinear halo orbit, or NRHO, a family of which you can see in this animation. Now, when Apollo went to the Moon, the low lunar orbit in which the command module waited was so pulled by the Moon's gravity that it was not stable and would not have allowed for the spacecraft to stay for long. But the near rectilinear halo orbit, balancing as it does between the Earth and the Moon, and glowing yellow here, means that the power and propulsion element only need to perform small orbit maintenance maneuvers to stay permanently. The gravity will balance. Okay. The near rectilinear halo orbit is different than those circular orbits that I mentioned that Kepler discovered, like the orbit that the Moon takes around the Earth. These 3 views here show you that the near rectilinear halo orbit is an orbit about the Earth, but at the distance of the Moon, so it's tugged by the Moon. And these Earth-Moon interactions mean that for every 2 orbits that the Moon makes about the Earth, the spacecraft, the Gateway, in this near rectilinear halo orbit will make 9 of these leapfrogs over and under the Moon. And the period of this near rectilinear halo orbit, or the period between these leaps, is roughly 6.5 days, with only 4 hours out of that almost week spent out of view of the Moon's south pole. Now, if you view it from the Earth, the near rectilinear halo orbit looks like a long elliptical orbit about the Moon, or a halo, thus the name. And this one has its closest approach to the Moon at the Moon's north pole, and its farthest approach at the Moon's south pole. And as I said, this near rectilinear halo orbit is one of a large family, and it was designed specifically to provide for maximum lunar coverage of the south pole, as well as to provide that a spacecraft in this orbit, the Gateway, stays in as much direct sunlight as possible. Now, near rectilinear halo orbits are very favorable for transferring into and out of, which is nice when your spacecraft is meant to be a staging area for exploration with other ships coming and going. And this trajectory animation shows the path that the Orion, with the crew in it, would take as they depart Earth, head toward a powered lunar flyby to put them into the Gateway in the NRHO, stay in the NRHO for 1.5 orbits before departing to head back to another powered lunar flyby to put them on the trajectory that would take them back home. Now, recall that the Gateway, with the power and propulsion element, is capable not just of holding place in one orbit, but also of transferring between orbits. The NASA Glenn Research Center Power and Propulsion Element Mission Design Team has designed several trajectories, taking the Gateway farther and farther from Earth to other orbits where mission scenarios and science can be completed. Flying these transfers will allow us to gain invaluable experience operating these types of large, human-tended systems in space, and along the lengthy transfers we're going to need to accomplish if we're going to be able to send humans to our closest neighbor, the red planet, Mars. Now, the current Artemis plans will take place in a two-phased approach, with the first focused on speed, landing on the moon by 2024, as we've discussed, and the second to establish a sustained lunar presence on and around the moon by 2028. Flying the gateway and the power and propulsion element will allow us to accomplish both the first by giving us a place to aggregate and assemble the spacecraft that will land on the moon, as well as the second by providing us a place to refurbish and refuel the lunar elements for subsequent lunar missions or reorient to focus on other areas on and around the moon. The current plans for Artemis have several elements that are similar to Apollo. The years may change, but the physics remains the same. First, the crew is launched in the Orion spacecraft on a Space Launch System, or SLS, rocket, on a trajectory that will take them directly to the NRHO, which you've already seen. Once the Orion docks with the gateway, the two crew members who will go to the surface transfer from the Orion into the waiting lunar lander system. Current concepts for the lunar lander system are composed of three parts. First, a transfer module, then an ascent module, and a descent module. The transfer module will take the entire stack and the crew to a low lunar parking orbit. From there, the descent module will take the ascent module with the crew down to the surface. When they've completed their mission, the ascent module will return the crew back to the gateway. Current plans have lunar surface missions roughly 3 to 7 days, after which the astronauts will return to the gateway, transfer back to the Orion, and make their way home.